So I'm getting 4x cubed plus 4x. Is that all right when I just do this right here? And then over here, this is plus 2x minus 4. So what do I get there?
4x cubed plus 6x.
4x cubed plus 6x what? Minus 4. Over that.
So do we want to see if the numerator was factorable?
Yes, hold on, yes. One of the twos. Oh, with the bottom, yeah. Like you could factor 2 out of this and then cancel, yes. I just want to make sure we have everything else right. Yeah? Okay. So now what? If that's our derivative. Find the critical numbers, right? So I have to do what with this fraction? Set the top to 0, and then also figure out where the bottom is undefined, right? Or where we might get division by 0? Yeah?
Yes.
Okay. So let's try setting the top equal to 0. We're going to run into a major problem here. D prime equals 0 means I need to let 4x cubed plus 6x minus 4 equals 0, right? That's what I need to do. I'll address that in just a second. What about where the derivative is undefined? Well, that would be where this down here becomes 0, right? Can the junk ever be 0? Can that junk ever be 0? No, because remember, isn't the square root of that junk, isn't that the distance between the 2 points? Isn't it? And can that distance ever be 0? Not if that point lives on that curve, right? So this is never going to be 0. So this is not going to be possible. But that is going to be not possible for us. So let me explain what's going on here. I picked this problem as just a random problem, okay? And hoping that we'd be able to get to an answer. We've done everything correct. There's nothing wrong in what we've done. The problem is, in order to figure out what this x is, we have to be able to solve this equation right here, right? And up to this point, we don't have a way of solving that. Now, the next section in the book is called Newton's method, and that's where we could actually solve that equation. But right now we can't. So is it okay with you if I tell you that, look, we can get the solution next time, next week? For now, let me just tell you what it is. Is that acceptable to you? Okay. But I'm going to have to refer to a computer to do it. This won't take long. Are you all following, what I've done so far? I was really hoping the algebra of that would work out a little better. But, hey, it is what it is. So I'm going to solve 4x cubed plus 6x minus 4. .5535 approximately. Approximately 0.5535. And that's the only critical number we have, right? And so what do we do with this? We plug it in and we compare the endpoints, right? But really, do we have to compare the endpoints? No, because we picked 2 points, right? 0 and 2, that we knew for sure the distance was further, right? Logically, looking at the picture. If I look at this point, which is what I get when I plug in x is 0, if I look at this point, which is over here when x is 2, my point had to be somewhere in here, right? And if I just got 0.5535, I'm in here, right? So what I need to do now is plug that into the function to get my y coordinate. And that'll be the point that's closest. So I'm going to already say that this is the x that gives you the minimum, all right? I'm going to say that just by, again, I'm thinking through the geometry of the problem. And so the point closest to 2, 0 on the graph of y equals x squared plus 1 is the point 0.5535, comma. Now, square that and add 1? Plug it into the function. Plug 0.5535 into the function. $1.306, yeah? 1.306. Questions? I mean, I understand I had to kind of wave my hands at that and say we can't do that. But if that had turned out to be like a quadratic, you could have done this, yes? All right. What we did not answer, this wasn't the question, right? Because the question said find the point on the curve closest. What if it asked you what is the distance? Could you do that? Could you figure out what the shortest distance is? You have 2 points now, right? You have the 2 points. 2, 0 is 1 point. This is the other point. Plug it into the distance formula. That's your distance. It's just a weird x and y, that's all. So why would we want to do something like this? Extend this into something like the Earth moving in its orbit around the sun and some big rock that's going through its own orbital path, whatever it's doing out in the solar system, right? And we have, through like Kepler's laws of motion, we have ways of modeling orbits of things, of moving bodies. So we have some equation or some relationship that gives us almost like this is a function, okay? And so what we would ask ourselves is like, where, like what's the minimum distance? Like how close is that going to get to us, What is going to be that minimum distance? Something like that. Or you have something like, that's even more complicated, is let's say you're trying to shoot down an airplane with a rocket from the ground. And so it's, you launch it and there's the plane flying and the rocket's going and it needs to know how to get to the plane, right? So it's constantly computing a trajectory, which is a function, and it's trying to find, okay, I need to meet it out there. It's trying to figure out minimum distances. I mean, there's a lot of computations going on. It doesn't, you just launch a rocket and it goes and finds, I like to blow up planes, and it just goes, right? I mean, there's a lot of mathematics behind that. And I guarantee it's got some calculus in there where it's computing minimizing distances until it actually minimizes it to the point where it's there, that sort of thing. I mean, it's obviously not that problem we just did, but it's the same ideas are behind that sort of thing. Does that make sense to you? Okay. Our desire to kill one another, right? Human beings, this motivates a lot of great mathematics and a lot of great science, doesn't it? We've done wonderful things with our need to be more efficient in killing each other. All right. Man, I mean, as you can probably tell already, there's really no limit to where we could go with this. I mean, you think about just about anything you want to find the maximum minimum of, and we can turn it into one of these problems. So I'll give you a choice on the next problem. We have, because I only have time for maybe one more. We have a river. We have a building over here, building A. We have a building over here, building B. We need to establish a secure hardwired link between these two buildings. Can't be Wi-Fi. It's got to be some, we're going to run fiber optic cable between these buildings. And we want to do it at a minimum cost, right? So we get some company out there and they tell us, well, look, it's going to cost you a certain amount of money to run this cable underwater because it's very expensive to put, waterproof housing for the cable underneath the water. So it's going to be very expensive to go through the water. It's a lot cheaper to go across the land. So how should we build it so that we use it costs the least? That's one problem we could do. The other problem is this one. I'm going to let you choose. I'm going to make a can. All right? And this can is for drinking beverages in. All right? Beer can, soda can, whatever you want. It's made out of aluminum. I'm going to manufacture these. I need them to hold a certain amount of liquid, like 12 ounces, right? But it doesn't really matter what the volume is. It just needs to hold some amount of volume, right? All these cans. How do I build that can so that I use the least amount of aluminum? Right? Think about this. I could build a can that holds 12 ounces that's like this, right? Or I could build a can that holds 12 ounces that looks like this. You're like, there you go, how you doing, right? Or you've got this big old flask thing, Or you could have one that fits in your hand. But we're going to say, forget the ergonomics of it, forget the human hand. Just if I want to build a cylinder to hold 12 ounces of liquid, what should the dimensions be so that I use the least amount of aluminum? Which of these pictures looks like it would use the least amount of aluminum? I mean, or I should ask you this. Do you think there's a difference in the amount of aluminum used in these three cases? Absolutely there is. All right? Think about a theoretical can that's like that. That's going to use a lot of aluminum, isn't it? Compared to one like this that's, you could get that to hold 12 ounces. It'll be really long, but the difference in aluminum usage is, there is a difference, all right? There is. I'm not going to go through it because we'd have to take specific examples and prove to ourselves, but it's not the same for each one. So which one would you rather see? The river with the fiber optic cable or the can? So let's take a vote. Fiber optic cable? Okay, can? All right, I think it's going to be the can. All right. How do we build a can which is going to be a right cylinder nothing that says a can has to be a right cylinder, so we're going to assume it's a right cylinder. How do we build a can, a right cylinder?
What is a right cylinder?
It's a cylinder that has a right angle at its base as opposed to something like this, where it's tilted over. So this is a right cylinder as opposed to a skewed, laid over. So this angle in here is obtuse. This angle from the side of the can to the bottom is a 90-degree angle. So how do we build a right cylinder with the least surface area, right? Surface area? That's what we want, right? The surface area is the aluminum, right? That's the part that we have to actually, buy from some aluminum company and build our cans from. So we want that surface area to be as small as possible. Yeah? How do we build a surface area? Question. All right, so let's come up with some generic unit of how much we want it to hold. And we're not going to use ounces because ounces is not a preferred method of volume. Let's use something like cubic inches or something. A cubic unit instead of like ounces.
Centimeters cubed.
Mm-hmm. Cubic centimeters. All right? That okay with you? All right. So we could make that number anything we want. So why don't we make it something that's really easy to work with, like 1. I mean, I know that we wouldn't want a can that holds 1 cubic centimeter, but we could make it easily then 10 or 100 or 1,000. Everything is just going to scale very easily. So we'll say, you want to go a little bigger with the can? You want to go maybe 1 cubic foot? Big can? No? You don't care. 1 cubic centimeter. Little tiny can, little Barbie can. Okay? So how do we do it? So objective, what is it that we're trying to optimize? Surface area. And we want the actual, what? Maximum or minimum? Minimum surface area. So the objective is to find the minimum surface area. Right? The minimum surface area. So I need an equation for it. Do you know the surface area of a right cylinder? Don't go to your page yet. Don't go there yet. Hold on. I want us to think through this because I don't have it memorized. But I can come up with it pretty easily, and so should you. All right? After you see this, okay? We know that we're going to need to know the radius, right? R? Got to know the radius of this thing in order for me to tell you anything about its area. I need to know how tall it is, so I'll call that h. Yeah? All right. If I were to take a hypothetical, imaginary, whatever you want to call it, pair of scissors, and I were to cut around the top edge, cut around the bottom edge, and pop those off, I would have 2 what? Circles, wouldn't I? So let's pop those off. Here they are. Circle 1, circle 2. What are the areas of those circles? Pi r squared, right? Each of these, pi r squared, pi r squared. What's still there to account for? This circular piece that no longer has 2 caps on it, right? Which looks like, oh, I've got paper here. Which looks like this because we've cut the top and bottom off, right? So now get your imaginary scissors and cut this open and lay it out flat. And what do you have? A rectangle, yes? There it is laid out flat. So what I've done is I've cut the tops, I've peeled them up, I've peeled it down, I've cut it up the side, and I've laid it open. Do you agree that's the can? All opened up? Okay, do you know, for a rectangle, it's length times width, or however you want to say it. Do we know any of the sides? I know this side, right, is what? The height of the can? But how long is this? It's, what it? 2R. 2R? Where are you getting that from?
Twice the radius.
Okay, so you're close. When I open this up, right, I'm looking for this length, but that's the same as the circumference of the circle, isn't it? Isn't that the circumference? Right, the distance from this around here is the same as the distance from here to here. So 2 pi r. This is 2 pi r. And so the area of the inner part there, the area of that inner rectangle is what? This times 2 pi r?
2 pi r.
2 pi rh. So what's the total area of the whole can? Surface area.
2 pi r.
So the area is 2 pi rh times plus
Plus 2 pi r squared.
pi r squared plus pi r squared, which is 2 pi r squared. Now, you can look that up in your book if you want. That's the formula you'll see. Okay? I've pointed out to students in the past the difference between memorizing something, or the difference between knowing something and understanding something. There's a major difference between those two concepts. If you know this formula, great. If you understand where it comes from, to me this is much more powerful than that is, than just knowing it, right? All right, so that's our objective equation, isn't it? We need the objective equation in terms of a single variable, though, so that we can turn it into a function. Right now it has how many variables?
2.
Well, the areas is, you could say, is one variable, but on the other side we have r and h, don't we? So we need to somehow get it all in terms of r or all in terms of h. This is where the constraint comes in. There is a constraint to the problem. What is the constraint? That's right. The volume is restricted here, isn't it? The constraint is that the volume of this thing has to be 1 cubic centimeter. And man, I'm debating. I'm going to let you decide. I like the idea that we're using 1, okay? And it's going to make a lot of the algebra in here a lot easier. But it would be so much more useful if we were to not fix the volume to be anything and just leave it as a constant. Like just say volume is something. Like volume is V. I don't know, whatever we want it to be. And then later on we could plug it in with 12 ounces or however, whatever. And not restrict ourselves to just the number 1. I'm giving you the choice right now. Do we want to just stick with 1, or would you like to change it to just an arbitrary value that you don't want arbitrary or 1?
It's arbitrary.
Arbitrary? Y'all okay with that? Okay, so V, the constraint is that V is fixed, right? I don't know what it is anymore. I'm not going to say 1. But remember, it's fixed. It's not a variable anymore, right? V is not a variable. It is a fixed number. I'm just not telling you what it is. Could be 20 cubic centimeters. It could be 40 cubic feet. Doesn't matter, but it's fixed. How in the hell am I going to turn that constraint into anything valuable over here?
Well, we know that V has to be bigger than 0.
Yes.
So that
Yep. But how is it going to help us eliminate h or r from this equation? Because I got to get it all in terms of r or all in terms of h, right? Is there anything you can tell me about the volume? What's that?
There's a formula for P.
That's right. There's a formula for the volume of a right cylinder. Now, do you know what that is?
Isn't it like 1/3?
That's a cone.
Same
This is h. Remember, this is r.
by R squared.
H times pi r squared. Now, you may have seen this formula in the past for the volume of a right cylinder, but think about what it's saying, okay? Again, this is more important. What's pi r squared?
Area of
The area of the circle. So isn't the volume just this area of that top piece times what? The depth of that can, isn't it? That's how you find the volume of something. You find the area of one of the faces and just multiply times how deep it is. Now it changes. If it's a cone, that's a problem. If it's a cone, then you can't do that because the area of the bottom doesn't stay the same the whole way through, right? It changes. And that's what you do in Cal 2. You can do that pretty easily in Cal 2. But, all right, so now how is that going to help us? I know that you just told me the volume Can I put a little, this is called a tilde. You ever seen a tilde before? A tilde is just a symbol that we use to distinguish something, to make it pop out a little bit. Like if I put V and V tilde, those are two different things. They're both connected to V somehow, but they're not the same. I'm only putting a tilde here because I want you to remember that that is a fixed number. All right, that is a number. Replace it with 10 right now, okay? Doesn't matter. What can I do with this equation?
Or you can divide it by pi r squared and just solve for h.
I could solve for h here, couldn't I?
Or you can divide it by pi.
And then plug that in over here for h. Or I could solve it for r and plug it in over here. No, thank you. I don't want to solve that for r, do you? Because you'd have to take a square root on both sides to get r. I think h is much easier, isn't it, to solve for? So let's solve this for h. So now I can come back from the constraint, I can come back to the objective. I can replace h with this, v tilde over pi r squared, then plus 2 pi r squared. Do you see any simplification I can do there? This pi cancel. One of the r's cancels. And so what's that first term now over here? A is 2 v tilde over r. And the other one doesn't change, right? 2 pi r squared. Have I accomplished what I set out to do here? Or do you remember what we were trying to do? I was trying to get the area in terms of one variable. Is it in terms of one variable?
Yes.
Yes, because v tilde is just a fixed number, right? So the only thing that's changing, or that's allowed to change right now, is r. So I can actually write this, a of r equals 2v, oh, you know what? I'm going to do something else. I'm going to write it this way. You tell me why I'm doing it this way. Why am I doing that? I'm about to take the derivative, right? So I'm setting it up for that. I brought the r from the bottom up as r to the negative 1 to make it a little easier to differentiate. Could you have taken this when you do the derivative? Could you have done quotient rule on this?
Yeah.
Yes, but you better remember that the derivative of the top is what? When you do quotient rule, derivative top would be here, what? 0, because v is fixed. V is a constant. So the derivative of that would have been 0. So you be careful with that. All right, what's next? I'm going to do derivative before that. Open or closed interval. Do we have any restrictions on this hypothetical can in terms of the radius? Is there a smallest radius we can have? 0? Right? I mean, it wouldn't make sense to have a negative radius here. But is there a largest radius we can have? I can make a very, very big can like this, right? All that happens is the bigger the radius gets, the smaller the height gets, right? And theoretically, I can go as small as I need to with the height. As r gets bigger, the height's just going to get smaller, right? So there is no restriction. I could have a can that's the size of San Antonio that's like infinitesimally thin, theoretically, yes? So I cannot restrict r. So I'm actually going to take r to go from 0 to infinity. The only reason I'm not using 0 is because if the radius is 0, you don't have a can, there's no volume at all. And I'm telling you that there must be some volume. Also, look at your function for a. Could r be 0? No. not within here, right? So this is open interval method, isn't it? You ready to take derivative? What is the derivative of this? What's a prime r? What is it? Minus, so here, minus 2 v tilde r to the negative 2 plus. And remember, there's no product rule, right? No product rule here. V is a number, so just ignore it. Derivative of that is negative 1 r squared, negative 1 r to the negative 2 times that. And then plus what? 4 pi r. And what do I need to do with this? Set it to 0, right? All that fun stuff. So where is this derivative? 0. Well, I'm going to rewrite the derivative for us. Why did I write it now back as a fraction?
So that you realize r can't be 0.
R can't be 0, yes. And the way that I've always done things in this class, I'm going to get a common denominator right now. Put those two fractions together. Okay, that's what I'm going to do. So I'll have negative 2 v tilde plus 4 pi r cubed over whole thing r squared equals 0. And that means all I have to pay attention to right now for figuring out where 0 is where the top is 0, right? And that means at negative 2 v tilde plus 4 pi r cubed equals 0. Move things around. This to this side, trying to solve for r. Divide by 4 pi. I'm going to reduce the fraction. 2 over 4 is 1/2. And what would my last step be here? Cube root. All right. So whatever your volume is, a critical number of this is that value. It's the volume of your can divided by 2 pi, take the cube root. Now, I have to figure out whether or not this is a minimum, though. How do I determine if this is a minimum? Oh, I didn't look at a prime undefined. Where did that happen?
0.
At 0. R is 0. But 0 is not in our interval, right? So I don't really have to worry about this. What were we supposed to do when we were on an open interval method to figure out whether or not we have a max or min? Make a number line. Draw a number line right now. But I'm only looking, what, to the right of 0? Not even considering over there. And I'm going out as far as I want. And I have a critical number here. But where's that? Where is that? We don't know what V is. So would you agree that I could just label it anywhere I want? Yes? What am I supposed to do next? Pick a test point. But how am I going to pick a test point if I don't even know what this is?
Now you can use sine v tilde.
I could, but I don't want to do that yet. I could do what?
Just go to the left and right.
Yeah, I can go to left and right, but you know, where though? I need something I can plug in, don't I?
That plus 1.
Okay, that plus 1 would be to the right. I agree. That plus 1 would work. I like that. That minus 1, I don't know, because what if this number is smaller than 1? Then it would take me into the negatives, right? So what's the number that's always to the left of a number?
The fraction.
twice.
how about half of it?
You can say,
Half of it?
yeah, tilde divided by 4 pi.
You could do that too. You could make this smaller, I mean, this bigger down here, which would make the whole thing smaller. So you can do you can do an infinite number of things. You could just take 1/2 times that. You agree that's going to be smaller? And then over here, yes, you could add 1. But instead, I'm just going to double it. And where am I supposed to plug that in? Those are my test points. Where am I plugging this in, those two numbers? Into the derivative, which is there. And all I care about is what? Whether or not it's positive or negative. So I'm going to go back to the derivative that we had when we had the common denominator. Wasn't it negative 2v, crap, what was it?
It's
V tilde.
it's negative 2 v tilde plus 4 pi r cubed over r squared.
That was our derivative, right? After we got a common denominator? I only want to know if this is positive or negative, right? What can you tell me about the bottom? Always positive. So I'm not even caring about that. I'm really just caring about this piece right here, right? And I'm replacing r with this. You ready to do that? I'd like for you to cube this real quick, right? That's what we're supposed to do? We're supposed to cube it? What would you get if you cube this? You have to cube the whole thing.
It would just be 1/2.
1/2 cubed, which is 1/8, times what happens when you cube the cube root?
Just comes out.
Goes away, so you're left with
v
v tilde over 2 pi. Everyone understand what I just did? If I plug that in right there, I cubed it, now hit it with what? 4 pi. And in front of that, I have what? Negative 2 v tilde? What happens to this?
Well, pi would be canceled.
Pi's cancel.
8 would be canceled, it would become 2. That'd be 4 pi.
1/4.
1/4 pi. Or
There's no more pi.
So v tilde on top, but, and then. but
That's just 1/4 v tilde, right? And over here I have negative 2 v tilde plus. And that's what? Negative. That's negative, right? I have negative 2 of these plus 1/4 of it. We know that the volume is a positive number. In fact, you could just factor out v tilde now. And you get negative 2 plus 1/4. That's a negative number. So when I plug this in, I get a negative, don't I? Which means that my function is decreasing. Now, that's what I was hoping for, right? Because now if I can show that when I go over here it's increasing, then that's a minimum, isn't it? So now we go and we plug this one in. What's the difference in that? We plug this one in. Put it in here. I'll do it up here. Negative 2v tilde plus 4 pi. Okay. Cube this.
Okay, well, then the 3 cubed would be 8,
8.
or 2 cubed, sorry. And then the inside would just be tilde over 2 pi. So.
Pi's cancel.
That'd be 2 times 8 would be 16.
So 2v tilde plus 16
Tilde.
v tilde. It's positive. So it goes up. That's a minimum. I have 1 minute. we reached the conclusion, right? I mean, we know where we get a minimum.
You plugged it into the regular question.
So yeah, please give me another couple of minutes just to try and wrap this up. Any questions on this? Okay, so we have a minimum. We have minimum surface area if, what, was it R? Yeah, if R is the cube root of v tilde over 2 pi. But I want the dimensions of the can. Right now I'm telling you what R is. What also do we need to determine? That's the radius of the can. The height, right? The height. What's the height of the can? So did anywhere in this problem, did we solve for h? What was our equation for h?
H is equal to v tilde over pi r squared.
Over pi r squared. Okay? That's what v tilde was? I mean, sorry, h was? Take this and plug it in for r, and you'll determine what, sorry, plug this in for h and for r, and you'll determine what h is. So let me try this. It's going to be pretty ugly, but let's try it. V tilde over, here's pi. Now I'm about to square this, all right, everyone? I'm going to square this, but it's already cube rooted. Isn't cube root the same as raising to what power? 1/3. So I'm supposed to take this to the 1/3 and raise it to the second. So isn't it this to the 2/3? So this is times, let me see, v tilde over 2 pi to the 2/3. And I know that that looks kind of messy. I'm trying to get to something here. I'm trying to get to a final result that I was hoping you would like, but this equals v tilde over pi over 1 times v tilde to the 2/3 over 2 pi to the 2/3. All I did there was split this into two pieces. And why would I have done that?
Yeah, because now you can multiply and then flip it.
Yeah, let me multiply and flip it, see if this helps. V tilde over, straight across here, v tilde to the 2/3 times pi, but then over, look, 2 to the 2/3 times pi to the 2/3. What do I do there? Split this up. Now, I only did that so that I could put this together. What's that? What's pi over pi to the 2/3? Pi to the 1/3. Also, I hate it when I'm out of time. Over 2 to the 2. What is 2 to the 2/3? I guess we can't do that. We'll just leave it. 2 to the 2/3. I'm almost to what I want you to see, okay? Are you all okay with me continuing this? I'm supposed to now, how do I simplify this fraction? I flip up?
Yeah, flip.
Okay, now keep in mind, this v tilde right here is really v tilde over 1, right? So when I flip, I get
2 to the 2/3 v tilde.
2 to the 2/3 on top, right? With a v tilde over on the bottom, v tilde, and then I have a pi here to the 1/3. I'll put it out front. And then v tilde to the 2/3. Can you do anything with that v tilde over v tilde to the 2/3?
So now you have v tilde to the 1/3.
V tilde to the 1/3. 2 to the 2/3 times v tilde to the 1/3 over pi to the 1/3. Almost there. Come on. Y'all got it. Give me just, I'm sorry. All right. Doesn't this mean, right here, doesn't this mean 4 to the 1/3? Isn't that the same thing? Right, that's the same as 2 squared to the 1/3. So aren't they all to the 1/3 then?
Yeah.
I have a 4 to the 1/3, a v tilde to the 1/3, and I have a pi to the 1/3.
So you can cube root that.
So I can cube root the whole thing. So h must be the cube root of, let's see, 4, and then what? V tilde over pi.
But it still doesn't help us because we still don't know what v tilde is.
Yeah, but now replace v tilde with anything you want. What was r? I'm going to put it up here with it. R?
R was the cube root of v tilde over 2 pi.
Okay, watch this. This, please, you got to give me this one more minute, I promise. Okay? Y'all got me? You ready? Magic time. See these two things? All right. Tell me what 2r is. Well, 2r is 2 times the cube root of v tilde over 2 pi, right? We know from earlier in this calculus class that if you have something outside of a square root and you force it in, it gets squared. If you have something outside of a cube root and you force it in, it gets cubed. If I force that 2 in, it becomes an 8, doesn't it? So doesn't this become cube root of 8 v tilde over 2 pi? And what's 8 over 2?
Then it's
4 v tilde over pi, which is actually h. Which means that if you want to build a can with the minimum surface area, you want the dimensions to be where twice your radius is equal to your height. But what's twice the radius? The diameter. Which means that your can should have the same diameter as it does height. Whatever your height is should also be your diameter. If you build a can that way, it has the minimum surface area. There's no other way to build a can and use less aluminum than to do it that way. So why don't they do it that way? It has a lot to do with the fact that it's not truly a right cylinder. You know, the top of the can has grooves in it, right? It's a different shape. The bottom has that dome in it. What's that dome at the bottom for?
What is that for?
When you put it in your car and you leave it in there, it's 105 degrees in your car. Pressure builds up, that dome pops out before it blows the can up. So it's not a true right cylinder. And so, of course, you wouldn't use that model. But guess what? I guarantee you, once they have some way of representing what they want to build, they minimize it, they find it. It has very little to do with your hand. It has more to do with the cost of the material. All right, so that holds for everything. That was a cool one that y'all chose because, is there a homework problem like that?
No, what is the homework?
Oh, what is the homework? Thanks for hanging out a few minutes. Man, where do you even go in here? There's just so many different things. 4.5, let's see. 7, 9, 10, 16. Trying to find some that are somewhat close to what we did. 25. Classic problem, another one, 27. Those are just problems to work on. It's hard to prepare yourself for anything in this section. Just remember the main ideas. You know, you have an objective equation that you turn into an objective function of one variable. You use the constraint to get that. You try and find the maximum. That's it. Now, as far as how the problem is presented to you, that's your job to get it from the word problem to this, to the calculus. This one was a little bit on the higher end of things as far as difficulty. Have a great Thanksgiving. See you next week. We'll wrap it up.